Hi guys, I'm Suprav. I go to Berkeley, and my partner Pragyan also goes to Berkeley, but unfortunately, he's celebrating Holi right now, so he couldn't make it. And we decided to do problem 3, the rope cup phone, and we did a little bit of a different analysis. So I hope you guys like it. So I think one thing that's interesting about like the physics curriculum is that regarding waves and stuff, it's all focused on E&M. So kind of switching to acoustics was an interesting experience to learn about. So in the acoustics world, people talk about impedances. It's actually the reciprocal. It's proportional to the reciprocal of the refractive index. So we can think of the rope cup phone as a signal passing through 2 different mediums. First, it passes through the cup, then it goes through the string, then it comes out the cup at the other end, right? Now the cup we can think about as a conical horn. The conical horn has an impedance given by this value here. The rho is for the density. The S is for the surface, the cross-sectional area of the small end of the cone. X naught is the length of the cone, and K is the wave number of the wave passing through. However, this is very simplified. It's for an infinite cone, an infinitely long cone. Sorry, no, it's for an infinitely long cone, and X naught is for like the mean. It goes like to the mean. There's like a, how do I explain this? So there's like a mean surface area that you can calculate, and that is the length for X naught. But it's all really simplified, and it doesn't really reflect in the real world. And the impedance on a string is given by the formula down below. It's the force in the y direction, which is basically the perturbation created by the sound waves that are coming through the cone, and the amplitude of the velocity in the y direction, which depends on the tension of the string. So we'll see an interesting relationship later. So our objective was to find 4 different parameters that we could adjust. So one was the rope tension, and the rest 3 describe the shape of the cup. So we decided to go with the cup bottom diameter, the top of the cup diameter, and the cup height, because we felt that that accurately described a cone shape. So our setup was to keep, we initially went with a vertical setup actually. I think Ron did it earlier in the day, he talked about it. But unfortunately that was too unstable for us to use. So we ended up going for the horizontal approach, where we kept cones at each side mounted on stands, and we hung a cup with weights inside. I used nickels because they're 5 grams. It's pretty convenient, and then that would pull it down over the edge and then of the stand, and then create a tension between them. On one end, I would put my headphones. I couldn't put my headphones and take a picture at the same time, but I would put my headphones here during the experiment. And on the other hand, I would put my microphone about where the ear would go when we were using a rope cup phone. Here's a schematic of what it looks like to make it more clear. The weight is attached to the cup and pulling down and over the stand so that there's a tension between the rope here. So our methodology was to adjust the tension by adding nickels to the cup so that we could keep the other variables constant and adjust this to see how it changes. And we used 3 different cups to analyze the other 3 cup dimensions. This was actually a problem for us because we couldn't adjust each variable regarding the shape of the cup without changing the others. Keeping the others constant while changing one would require making new cups and stuff, which was not feasible. So we had to come up with a new method of trying to interpret data where we could not keep the other variables constant. So I put the tone at the one end with the headphones and recorded it at the other. This is an example of what the data looked like zoomed in. One of the bigger changes was that the amplitude went down, and there were also changes in distortion, or there were also distorted values in the frequency, which you can't see zoomed in. And these are the values we tested for, where I put the sound through and recorded. We tested different tensions, and then we tested different cup sizes. I mentioned that we had 3 cups earlier, but you can see that we have more values. The reason being is that for each cup, I could create a new cup by cutting the top off the cup so that we have different dimensions. That would keep the bottom diameter of the cup the same, but we have new top diameters and new cup heights that we can use for our data. So we decided that we were going to weigh the amplitude and the frequency half and half in our assessing of the quality. So the amplitude we found by just taking the average of the wave. Like you can find the amplitude of the wave and take the average of that. The mean output frequency, we had to use a Fourier transform to find the output frequencies of the signals coming in. The mean input frequency is just 441 hertz because that's the signal that we fed in, the pure tone. So here's an example of when we applied a Fourier transform to the input and output. Here it's very clean, right? Because it's all 441 hertz. Here there's slight deviations from the norm, but for the most part, it's still 441 hertz. So because we couldn't keep the other variables constant, we had to opt for a machine learning approach for this multivariate data. That's because a machine learning approach can take all our different data points and give us a final answer as to what the quality is given all the data we have. So it'll form a neural network and then take whatever you put in and give us a predicted quality out. So using this, we were able to find the general trends of what was going on. Something else I want to, yeah, thanks. And I should mention my partner did the machine learning, by the way, so I can't talk too much about it. This is the model he used. And for the dimensions, we had 5 different dimensions, 3 for the parameters that describe the cup shape, 1 for the tension, and 1 for the time. And these are our results. They're not the cleanest. And we weren't able to find a clean numerical values that describe the trends that were going on. We think this is because we didn't have enough data points. Machine learning tends to take a lot of data. And we also think that this could also be because of precision error, because the cups weren't very small compared to or the cups weren't that big compared to our rulers. So an error takes, it's a little significant, an error in the measurement can be kind of significant when putting it into our model.
Unfortunately, your time is up.